So here we have the standard normal distribution problem. The goal of this problem is to determine and to derive the standard normal distribution density function. So to start with, we have some facts from statistics. The requirements for a probability density function include that the function must be greater than or equal to 0 for all real numbers, and that the integral from negative infinity to infinity, which covers the entire xy plane, of f of x dx is equal to 1. Let's get started. So first, we know that n of x, or the normal distribution density function, is equal to k e to the negative x squared over 2 for some value of k. We also know that because e to the x and any exponential function of that form, n of x must be greater than 0, which already checks our first requirement. The second requirement, however, is that we need to determine that from negative infinity to infinity, the integral of n of x dx is equal to 1. Let's begin by plugging in our values. So now we have the integral from negative infinity to infinity of n of x dx is equal to the integral from negative infinity to infinity of k e to the negative x squared over 2 power dx. We can move the constant in front, making this equal to k times the integral from negative infinity to infinity of e to the negative x squared over 2 dx, which we also know is equal to 1. Right now, we cannot solve this problem because e to the negative x squared over 2, the integral of e to the negative x squared over 2 dx, cannot be solved as we have nothing to use substitution for and there is no formula for this yet. Let's simplify this problem. First, we can divide both sides by k, which is the equivalent of taking the inverse of this integral. Now we have 1 over k equals the integral from negative infinity to infinity e to the negative x squared over 2 dx. From here, we can square both sides. This way, we can start to work towards a problem that is solvable. Now we have 1 over k squared is equal to the integral from negative infinity to infinity of e to the negative x squared over 2 dx squared. This is the same thing as the integral from negative infinity to infinity of e to the negative x squared over 2 dx times itself, where x can be any variable. As such, we can substitute x equals y into this problem for one of the x squared variables. Now we have the integral from negative infinity to infinity of e to the negative x squared over 2 dx times the integral from negative infinity to infinity of e to the negative y squared over 2 dy. This becomes a double integral, with both integrals integrating over the region of negative infinity to infinity of e to the negative x squared plus y squared over 2 dA. From this, we can simplify into polar coordinate, to become an integral which we can integrate over. The important equations we will need to know is that x squared plus y squared equals r squared, and that negative infinity to infinity for both integrals is the equivalent of integrating over the entire region 2, which, in the polar coordinate plane, is the same thing as integrating theta from 0 to 2 pi and integrating r from 0 to infinity, as r is the coordinate, or the distance, from the origin point out. It's also important to note that dy dx, which is equal to dA, is equal to r dr d theta as we translate into polar coordinates. Using these formulas, we can rewrite our equation as the integral from 0 to 2 pi times the integral from 0 to infinity of e to the negative r squared over 2 r dr d theta. Now we can use substitution as we have that r that is outside of our e to the exponent. If we substitute u for u equals negative r squared over 2, du is going to equal negative 1/2 times 2 r dr, which is equal to negative r dr. Now we can integrate over our region. Integrating, substituting, we result in the integral from 0 to 2 pi times the integral of a to b of e to the u du d theta, which is equal to the integral of 0 to 2 pi of negative e to the u, evaluated at a, b, d theta. This is equal to the integral of 0 to 2 pi of, now that we substitute our u back into the equation, negative e to the negative r squared over 2, evaluated at 0 and infinity d theta. A couple of important things to note is that the limit as b approaches infinity of negative e to the negative b squared over 2 is the same thing as the negative e times the negative infinity squared over 2 power. This will become negative e to the negative infinity, as infinity squared and infinity divided by 2 are both still equal to infinity. This can be simplified as negative 1 over e to the infinity power. This means that e is being put to an increasingly large power. That becomes 1 over an increasingly large number, which becomes an increasingly smaller decimal, negated. That approaches 0. It's also important to note that any value to the 0th power is equal to 1. Now we can simplify our equation. Now we have the integral from 0 to 2 pi of 0 minus negative e to the negative 0 squared over 2, which will become negative 1, d theta. Remember that 0 comes from the limit of b as b approaches infinity of negative e to the negative b squared over 2 power. This simplifies, our integral simplifies to the integral from 0 to 2 pi of 1 d theta, as 0 minus negative 1 is equal to positive 1. Now that we integrate, we have theta evaluated at 0 to 2 pi. This is equal to 2 pi minus 0, which is equal to 2 pi. Remember that that equals 1 over k squared, as we determined earlier. Since 1 over k squared is equal to 2 pi, 1 is equal to 2 pi times k squared. This means that k squared is equal to 1 over 2 pi. If we take the square root of both sides, we end up with the square root of 1 over 2 pi is equal to k. Note that the k function was originally positive and then we squared it, so as we're taking the square root, we are only taking the principal root, which means that k is only going to be equal to the positive square root of 1 over 2 pi. This can be broken up into the square root of 1 over the square root of 2 pi. The square root of 1 is 1, and the result becomes 1 over the square root of 2 pi is equal to k. Now we can plug this into our original function, n of x is equal to k times e to the negative x squared over 2. This becomes, as we substitute in k, 1 over the square root of 2 pi times e to the negative x squared over 2. And that is our standard normal distribution density function. Thank you.